So thank you everybody for coming today. I appreciate you all taking the time out of your busy schedules to come to this talk. So today what I wanted to talk about was the challenge that artificial intelligence and machine learning puts on the network and how we as Cisco Silicon One can help solve those problems. Now, if you think about the web scale network, we tend to focus on what I would call the front end network. This network is really designed to connect general purpose x86 or ARM-based servers to each other, as well as to the outside world. And the bandwidth of this network is growing at a very fast pace because of the migration of applications from on-premises to the cloud. Now, the web scalers have been able to keep up with this bandwidth growth, both by relying on sort of traditional year-over-year growth of server compute, as well as networking. And within a generation, they scale out horizontally to this network. The interconnect in this network is all general purpose Ethernet, which as we all know has an absolutely massive investment behind it. And that means that basically roughly every 18 to 24 months, the bandwidth of the network switches doubles. What we tend to miss when we talk about a web scale network is a secondary network that's called the back-end network. Now this network is really designed to connect specialized types of compute and endpoints together and not actually connect back to the outside world. This network was historically driven by high-performance compute or storage applications, but more recently what's driving the bandwidth in this network is actually the explosion of AI and ML-based workloads. And that's actually creating a step function increase in the amount of bandwidth that these networks need to be able to deliver. And so the web scalers are certainly still relying on the year-over-year growth of GPUs as well as networking equipment, but it's resulting in a massive new build-out of infrastructure to meet these needs. And because of that, many of the web scalers are moving away from proprietary interfaces like InfiniBand and moving towards a more generic interface like Ethernet. Now, it's clear that because the needs are different, it's not surprising that we actually need a different solution for AI ML than we use for high-performance compute. Now, interestingly enough, we've actually seen this migration happen once in the past already. It used to be that the storage interconnect was all done on the back-end network, but with the arrival of RDMA over converged Ethernet, that workload moved from the back-end network to the front-end network. So let's begin to start to understand what makes the AI ML workload different than sort of the traditional data center traffic. To understand that, we really need to look at how does AI and ML workloads work. So there's a bunch of computation that happens on the GPUs. And these GPUs are very high performance, and so they're actually able to saturate network links quite easily. After they finish their computation, what they do is they send the results to other GPUs associated with that job. Now, there's many ways that they do this, but in the interest of the time, I'm really only going to focus on the all-to-all collective. And the way this works is basically every GPU in a job sends the results to every other GPU, and you get a full mesh traffic pattern going on. Now, interestingly enough, there's an added piece here where there's a full synchronization event. And what happens is the GPUs wait for all of their peers to receive the data before they start again. And what this causes is basically a stall of GPU resources waiting for the slowest path in the network to complete. And what we do is we actually measure something called the job completion time, or JCT, and that's really based on the worst case tail latency through the network. Now, if you think about the traffic patterns here for a traditional data center, really it's made up of many asynchronous small bandwidth flows who start and stop at their own time. And this creates a pretty chaotic pattern of the network. But if you look at the cumulative load across the network, it's actually reasonably constant. That's very, very different from this AI all-to-all collective traffic pattern, where because things are synchronized, all of the GPUs start transmitting at roughly the same time. They send out their data. Depending on the latency of the network, they start stopping their transmission, and then everybody stops and starts again. So you actually have a few number of very high bandwidth synchronous flows through your network. And because you're sitting here waiting for all the GPUs to finish, your compute is sitting there idle for a large portion of this. This notion of synchronization really, really magnifies the long tail latency effect and bad load balancing decisions within the network. So in my view, I would contend that the network is actually fundamental, and if you make a single wrong path selection, you solve the entire AI job. So let's now talk about why is AI and ML different from high performance compute. If you think about what high-performance compute really is, it's a large disaggregated computer system who's really working on one job at a time. That's quite different than something like an AI ML infrastructure in the web scale, which has a huge hardware infrastructure running many, many jobs all at the same time. And it's pretty easy to understand that there'll actually be interference between these jobs. And because all of these GPUs have this synchronization effect, as you get interference between jobs, this interference causes the job completion time to slow down and really becomes very, very visible. So again, to reiterate here, the tools that we've relied on in the past for high-performance compute do not scale to meet the needs of AI ML, and we as an industry need to understand that and work to solve that together. So if I oversimplify for a second, the traditional front-end data center network is mostly what I call compute-bound. As you look about high-performance compute, I would say it's still mostly compute-bound, but some amount of network effects start to come into play. But when you think about AI and ML network loads, if you don't design your network correctly, I would contend that it actually becomes mostly network-bound because of this notion of synchronization. Now, it's all fine for me to talk about this in abstract, but I think it's much more powerful if we actually look at real data to understand how this stuff works. So what we've done is we've actually built a very small AI ML cluster with 256 200 gig GPUs, 32 GPUs in a rack with a top-of-rack switch. So there's 8 top-of-rack switches, there's 4 spines, and it is a non-oversubscribed network. And what we're going to do over this network is we're going to run this all-to-all collective that we talked about before. And again, if you remember the way this works, every GPU is sending to every other GPU in the job. The traffic is interleaved to each one of the destinations in a round-robin fashion. And the transmission starts at roughly the same time. What we'll then do is we'll measure the job completion time. And remember, the job completion time is when the last bit of data on that job actually receives its transmitter, or is received at its far end point. So the first thing we'll study in this infrastructure is what happens as we start to increase the number of simultaneous jobs running on this infrastructure. Okay? And what we'll do is we'll compare standard Ethernet ECMP, which uses a hash-based structure to select the link, and we'll compare that to a fully scheduled fabric. Now, when I say fully scheduled fabric, what do I mean? I mean it's got an ingress VOQ, a request grant infrastructure we spray across all of the links, and we reorder at egress. And we'll take these two data points and we'll normalize it to what I would call the ideal job completion time, which is how long does it take to transmit that number of bits at the Ethernet rate that we're using, ignoring any fiber latency and any switch latency. So clearly, you can never actually reach the ideal job completion time, but it gives us a floor for us to sort of target. So let's start to look at the results. So if over those 256 GPUs, we run a single job, what we end up seeing is that for Ethernet ECMP, you get actually pretty close to a pretty good job completion time here, where it's only 24% slower than the ideal job completion time. If we compare that to a fully scheduled fabric, though, we actually get to 9% of the job completion time, or a nearly perfect performance result. But as we scale this out from one job over to 16 jobs, what you actually see is a perfectly linear response to a fully scheduled fabric. Or said more simply, with a fully scheduled fabric, it is irrelevant to the number of jobs that is running over your infrastructure because of the exceptional load balancing and scheduling characteristics. If we look at Ethernet ECMP, what you see is as you add the number of jobs to that infrastructure, you start to see that job-to-job interference that we were talking about earlier, and the job completion time ends up stretching out to the point where it's actually 2.1 times slower than the ideal. Or if you compare it to fully scheduled fabric, a fully scheduled fabric actually gives you a 1.9 times quicker job completion time than standard Ethernet over ECMP. Now, that's not to say that we can't actually improve standard Ethernet, and I think that's really, really important for us to understand. So the goal of using, for example, telemetry infrastructure over Ethernet is to extract information from the switches, have the switches talk to each other, the switches talk to the hosts, and the goal is to actually bring down that curve from the top. Now, we're never going to reach the point of getting to the ideal job completion time, but hopefully we can get close enough to allow that to be useful for our customers. The second thing that we study here is how much network speed up do we need to add to improve the performance of standard Ethernet. And again, what we'll do is we'll compare that, the Ethernet in blue to the fully scheduled in green, and compare that to the ideal infrastructure. And the way we're going to be adding speed up to the network is we're actually going to be idling some of the GPUs of the infrastructure below those top of rack switches. So what do we see? So we start off by taking the last results that we just talked about with 16 jobs. That is now our baseline here with a one-time speed up and 256 GPUs. As we add a 33% speed up to the network, what you actually see in the fully scheduled fabric is you get a 1.01, or actually I would contend a truly perfect result. ECMP clearly gets better, but as we get to a 2-time speed up, we actually get to the point where Ethernet gets to a 1.19%. So it's actually pretty good, but obviously it's 19% slower than the ideal, and we've had to do a 2-to-1 speed up to get there. Now, if we compare on the left the 1-time speed up with fully scheduled fabric to the right with a 2-time speed up of ECMP, and we think about what that really means for a second. Remember, with those top of rack switches with a 1-to-1 speed up, we're putting 32 GPUs below every single top of rack switch, and we're getting the job completion time of 1.11. If we compare that to the Ethernet ECMP case, where we've had the 2-time speed up, the way we've done that is we've actually shut off half of the GPUs below the TOR. So you only get 16 GPUs, and interestingly enough, the job completion time is actually still worse than the case of fully scheduled fabric. Or said more simply, if you use a fully scheduled fabric, you can actually achieve, for the same networking infrastructure, 2 times more compute. Now, if we look at this middle case and trying to understand a little bit more about what's happening, let's sort of take that next step. If we look at the infrastructure and we look at the network and how it communicates back to the GPUs, it has to send flow control in order to throttle the GPUs periodically. So what we plot here along the x-axis is a histogram showing the ranges of time that each one of these GPUs have been x'd off. And the y-axis, we show the number of GPUs that have fallen into that bucket. So what do we see when we start to play those apart? But 6 out of 192 GPUs, or about 3% of the GPUs, never received X off, which is fantastic. That means those GPUs were never stalled in their transmit. But unfortunately, what you actually see is 9 of the GPUs are stalled for 1.25 milliseconds over this test period. And the way I think about that, what does that really mean? Because of this synchronization effect, it means that 5% of your GPUs being stalled for 1.25 milliseconds stalls the other 95% of the GPUs in your infrastructure. And if we remember here for a second, the any-to-any collective that we're talking about is actually inherently non-blocking. So the traffic pattern that we're putting into the network never causes oversubscription. So what we're seeing here is actually the effect of the network making bad load balancing decisions, dragging everything out and throttling back those GPUs. If we compare that, on the other hand, to the fully scheduled fabric, what you see is actually that no GPU ever received X off at any point in that test, which means that it is a true 100% non-blocking fabric. Okay? And that is why we're able to see this ideal job completion time when we use a fully scheduled fabric. So if I think about the full solution space here for a second, I think there's really 4 possibilities for interfaces for us to use. There's InfiniBand, there's Ethernet with ECMP, there's Ethernet with telemetry assistance, and there's a fully scheduled fabric. So if you think about InfiniBand for a second, what's the problem with InfiniBand? It's a sole source proprietary technology with a reasonably limited investment behind it. And that means that it's falling further and further behind the generic Ethernet switching infrastructure. And therefore, you have to add layers to your network to get the same bandwidth out of that infrastructure. That drives up network costs. But its performance for a single job is actually very, very good because that's what it's designed for. But as you start to add multiple jobs on that infrastructure, it begins to slow down. If we compare that to standard Ethernet for a second, it's almost the polar opposite in every respect to InfiniBand. It is fully open. It has a massive investment behind it. And all of that is incredibly good. what you end up seeing is that for a single job performance, it's also pretty good. Where it starts to struggle a little bit is with that multi-job performance, as we saw in some of that data previously. The goal of using something like the telemetry-assisted Ethernet is to improve that multi-job performance. And finally, with a fully scheduled fabric, it is clearly not as open standard as generic Ethernet, for sure, but there are multiple vendors who do support this type of fully scheduled fabric infrastructure. And clearly, depending on which vendor you end up using, you can get different cost dynamics within your network. Now, I've talked here a lot about all of this stuff in abstract. Now I'm going to switch gears a little bit and talk about how can Cisco Silicon One help us solve these complicated problems. So in Cisco Silicon One, we have a few different modes we can run our devices in. We have what we call standalone mode, which is we take every SerDes around our device and we convert it to standard Ethernet. And you can build a leaf-spine topology using Ethernet. We can use telemetry import and export from our devices to improve the performance, as we talked about earlier. We also have two other modes available in our Cisco Silicon One architecture. We have what we call a line card mode, which is where half of the ports are Ethernet and half of them are fully scheduled fabric. And we have a fabric element mode, which is where all of the SerDes are a fully scheduled fabric. And you can run the fabric element on the spine, the line card mode on the leaf, and get this fully scheduled fabric that we were just talking about. Now, what's very interesting here is actually the same hardware that you deploy can be software configured either into the left picture or the right picture. And so if we think about what that means for a second, out of those 4 choices that we talked about, you can deploy a Cisco Silicon One topology and take any of the 3 of these devices, all based on software-based configuration. And our goal here is to allow our customers to evolve their network as they see the needs to, depending on their requirements and what evolves over time. So you can start with Ethernet, move towards fully scheduled fabric, or you could go the other way. You could start with fully scheduled fabric and move to Ethernet. Now, I'd actually like to invite my friend Omar on stage with me. Omar is the director of DC networking. I had the pleasure of being on stage with him last year at OCP, and I'm thrilled to have you this year with me today, Omar.
Yeah, thanks. Thrilled to be back up here again with you.
Fantastic. So I was hoping to get your thoughts on the challenges of AI ML and how Meta thinks about it and where your guys' minds are at.
Yeah, I think you've captured a lot, and we're spending a lot of time on this. Actually, it's an exciting time in networking. If I rewind even just a few years ago, it's like, okay, I'm keeping up with speeds and feeds. I'm getting up new, the latest chips and kind of keeping up with those. But largely, the applications in the front end, as you covered, were Poisson in nature, so they would scale with the bandwidth and everything was good, right? But now these workloads come on and we're seeing performance problems. And I've been around networking as you have for many years, so hey, I think networking folks love a performance problem. Let me go analyze it. Let me go see the bottlenecks and all. And that's what we've found. We've had to bring, elephant flows or self-similarity or queuing techniques. All these things are coming together to improve the performance for what is a critical workload for many of us.
Fantastic. Well, I got to say, Omar, the partnership that we have to me is incredibly valuable, and I love working with you and your team, and I hope we can continue to do that in the future.
Yeah, no, thank you, though. Ever since we announced the partnership publicly last year, we've been doubling down on it and investigating such use cases such as this. And I'm really hopeful and excited that the Ethernet and scheduled fabrics is going to be a really important lever in our future fabrics.
Awesome. Thank you so much, Omar.
Thanks again.
Appreciate your time.
All right.
Thanks. Take care. I'll see you next year.
Sounds good.
So just to wrap it up in my last few minutes here. So what are the key messages that I want to make sure that you all take out of this talk? So the first is that the network is fundamental when you start thinking about AI and ML, and it's really based on the traffic characteristics that AI and ML require. If you think about the data center front-end network, right, that is really built out of many small asynchronous flows, and so a penalty for making a bad load balancing decision isn't great, but it's really not that bad either. if you think about the AI ML network, again, it's almost the polar opposite of that front-end network. This is built out of a few large synchronous flows. And because of that, in conjunction with the fact that there's this notion of synchronization, if you make a bad load balancing decision, your AI compute stalls. That makes AI ML mostly network bound if you don't actually design it with the right network. Again, just to remind ourselves, I think InfiniBand did an amazing job for high performance compute, but I don't believe it's the right interconnect for AI ML because of its slow pace of innovation, the proprietary interconnect, the fact that it is expensive, and that it's really optimized for one job. And if you think about, again, a web scale AI ML infrastructure which is trying to run many jobs, that's quite a different problem to solve. Now, when I think about Cisco Silicon One and what we can do, because we have this flexibility of how to run our hardware infrastructure, the question that I get a lot is, what type of customer should use Ethernet? Or what type of customer should use fully scheduled fabric or something else? So if I try and boil it down for a second, for the customers who should be using Ethernet, these are the customers who really want to enjoy this notion of a very heavy investment, open standards, and very favorable cost and bandwidth dynamics of Ethernet, right? There's a lot to be said for the open standards of Ethernet. For those customers who are willing to invest in the infrastructure for telemetry and the connections between the GPUs and the network to try and improve those load balancing decisions, to again flatten that curve as you add more jobs to the infrastructure. Or for those type of customers who are willing to carefully place jobs on the AI ML infrastructure to try and improve some of those load balancing decisions. Who are the types of customers who should deploy the fully scheduled networks that we talked about? I think it's the type of customer who's really sort of very focused on trying to reap all the benefits of performance from the network, who are interested in that ingress VOQ, fully scheduled spray and reorder type of fabric, which gets you, as we've shown in these slides here, 1.9 times faster job completion time, and or 2 times more compute for the very same networking infrastructure. Now, again, I think there's a lot of people who can help solve this problem, but I think Cisco Silicon One is very unique in the industry in the fact that we can give you the same cost and power dynamics as Ethernet, but with a fully scheduled fabric on top of it. Nobody else in the industry can do that. We have the unique capability that we have one architecture that can be configured towards Ethernet or fully scheduled fabric. We're also unique in the fact that we use P4 programming to allow our customers to build the telemetry semantics that are important for them on their network, allowing them to add features over time. And although we didn't talk about it here, it is really important on how the buffering schemes work in the silicon architecture when you think about burst absorption and avoiding flow control style scenarios. So Cisco Silicon One, again, is very unique in the industry in the fact that we have a fully shared and fully unified packet buffer. So what I will leave you with is that Cisco Silicon One, in my opinion, is the one architecture for AI ML. It can do Ethernet, telemetry assist Ethernet, or fully scheduled fabric. So thank you very much. Does anyone have any questions? Would you mind moving to the mic?
Any thoughts on cell-based? Would cells help or not help? Or?
Yep, so it's a good question. So obviously there's different ways you can do a fully scheduled fabric. If you ask my opinion, if I was to design a fabric architecture 15 years ago, I definitely would use cells. And why would I do that? I would do that because SerDes transmission times are very slow, and the amount of memory that you could put in a piece of silicon was very limited. And so I would invest what are called silicon die area associated with the segmentation and reassembly of cells. Fast forward to today, a lot of things have changed. SerDes speeds have gone from 1 gigahertz to 50 gig or 100 gig SerDes. Memory is now free with silicon process technology advancement on the die. Those two dynamics mean that there's actually no benefit whatsoever to cells. What you really care about is the spraying and reordering. So what cells is costing you now It's costing you dedicated logic to do the segmentation and reassembly, and it's also prohibiting you from doing what we talked about earlier, which is having a unified architecture, being able to be fully generic Ethernet on all of the SerDes, or half fully scheduled fabric, half Ethernet. Did that answer your question? Great. Any other questions? Well, thank you all for your time. Enjoy the rest of your time at OCP.